Welcome to the last live session, week 12 live session of molecular spectroscopy of physical chemist perspective, NPTEL live discussion session. So today we will what we will do that we will try to solve the, the assignment problems from week 12, and then we'll again try some numerical problems from Atkins book, and then we will try to wrap up. If there is time permits, then we'll try to wrap up with a revision, quick revision from the we'll go to the website, and we'll from week by week we'll try to I will try to give you quick idea or quick revision, you can say, if time permits, and then we'll stop it for this course. And hopefully you are having a good time. So let us begin. So anyway, I hope you are, as no one is there in this live decision session, I believe you are watching this in YouTube. The recordings is there in YouTube, and also the slides and the notes will be available with a separate drive link that will be provided you to by the NPTEL team. I think it is already there in the Swayam portal. You can see that. And here is the electromagnetic spectrum. See that we have started with microwaves, right? The rotational spectroscopy, where at the frequency is around 10 to the power 8 hertz, and the wavelength is longer, right, in the portion, as you can see. Then we have moved to the vibrational spectroscopy, where the energy is bigger than the microwave spectroscopy and wavelength is less for this particular place. And then there is visible region that we can see actually. If from in nanometer scale or in wavelength scale, you can say the energy is between 350 or 400. From 350 to almost 750 nanometer is the range of the visible light. And then comes ultraviolet ray, UV ray, the UV visible. That actually this UV region UV region has higher energy, and that is the one of the harmful part of the, we generally say, right, that these UV rays are bad for our health and other things. So these are a very high energy actually. And then come X rays, and then gamma rays, having the highest energy and the shortest wavelength. So this is general A, and you can see at the leftmost part there is radio waves, and with the in this spectrum that has the lowest energy, means low frequency but highest wavelength. These radio waves we are dealing right now with the NMR spectroscopy, right? So there the energy gap is very less. So we are going to solve a numerical problem where this energy gap or this population of this energy gap we will discuss in one such problem. I hope you can hear me and the recordings is coming clear. Let us move to the assignment 12 problem. First we'll start with this. There are 6 or 7 problems, and we'll try to already the solution is with you. We'll try to discuss them. So the first question says the factor or factors that contribute to the non-observation of fine structure in NMR spectrum due to coupling between equivalent nuclei is or are. So firstly, that equivalent nuclei are going to couple, but you can't really see the coupling, right? Because there will be that, I think, the change in the destabilization will be same for all three. Actually there are 4 states, but possible state, but in all three of them will be, all three of similar spin multiplicity are going to destabilize by the same amount, so you are not going to see that. And another thing is, so the first answer will be indistinguishability of the nuclei. Of course, it is one of the right answer. And the second is the mixing of alpha 1 beta 2 and alpha 2 beta 1 wave function. When the coupling is not there, the energy of that alpha 1 beta 2 and alpha 2 beta 1 are at 0. You can set them as your reference point, and then you see that when the coupling is there, one of them, one of the plus alpha 1 beta 2, actually what is going to happen, the how the states are going to look like, one will be the linear combination plus and another will be minus. So I don't exactly remember. I think the minus will be destabilized by stabilized by minus 3 h by JAA, something like that. I exactly don't remember that. And another will be destabilized by HJ by 4 some factor, right? And so those mixing actually is going to be one of the reason that you won't see any coupling between them. Okay. And JA of course is not zero. It is there. There is some coupling. Now the second problem, the X component of nuclear spin angular momenta do not contribute to the coupling between what is the question? The X component of the nuclear spin momenta do not contribute to the coupling between non-equivalent nuclei, equivalent nuclei, equivalent as non-equivalent nuclei, nuclei with integral spin quantum number. Actually, the right answer is non-equivalent nuclei. Okay. Now the third question. The rotating frame of reference is used to record the NMR spectra in order to account for the precessional motion of the bulk magnetization vector around. The answer is actually the axis of external magnetic field, but which is also a z axis. So actually, your answer are two of them are correct. Okay. Now let us go to the fourth question. The 90-degree pulse is required to record the spectra in FTNMR so that the absorption and emission are separated, monochromicity is induced, bulk magnetization vector has a component along the detector, and bulk magnetization has a detector vector along a component along the radio frequency. Actually, the third option is correct because you remember if your external field is along z axis and you are applying an B1 along the y-axis, then your actually along the x-axis your detector will be there, and it will have a and it should have a component to be detected along the x-axis, that is the detector, so that we use a 90-degree pulse. Okay. Now the question number 6. 90-degree tau means the some relaxation time, then 180-degree pulse sequence hence measure spin lattice relaxation, measure spin relaxation is associated with inversion recovery and is associated with spin echo. If you remember, the 90-degree tau 180-degree pulse sequence is actually associated with the spin relaxation, right? And which is also associated with the spin echo, right? So you remember 90-degree. So first, when there is the bulk magnetization is looks like something like it is around all of them, right? It is around all of this. So when you apply and 90-degree pulse, it will actually comes like this, only along only one direction, which is in xy plane. Maybe I will draw it better. So in xy plane, it will look like something. The bulk magnetization will be something like that, right? So this is your y-axis and this is your x-axis. This is your bulk magnetization vector. Now when you give it to relaxed state, so it will what it will do? It will, due to magnetic inhomogeneity and due to different the environment of that thing, it will precess differently. Different nuclei will precess differently. Some will precess fast, some will precess slow. So this is for the slow, this is for the fast. So this is this side and this will precess like this. Now you give an 180-degree pulse so that your the debunching that has happened already. So rebunching will take place. So during this, your slow will come here and fast will come here and it will move like this, right? So the rebunching will takes place. So it will come here and this will come this and rebunching will takes place. So it will look something like this. But the thing is, now the magnitude will be less. So this is how the spin echo will look like after some time t tau. it will decrease exponentially e to the power minus t by tau 2. Tau 2 is for spin relaxation, and for spin lattice relaxation it was 180 degree tau, and then 180 degree tau, and then 90 degree. One minute please. Okay. Now the last question is 90 degree tau 180 degree pulse equation. Pulse sequence removes the effect of one inhomogeneity in magnetic field, different chemical shifts, spin lattice relaxation, and spin relaxation. So the first two I said that what caused that debunching of that thing, that is one inhomogeneity of this magnetic field and different in chemical shift. So this effect will be removed by that 180 degree pulse. Okay. Now, as this thing has been done, so we'll go directly to the some numerical problems for the Atkins of NMR spectroscopy. Okay, so let us do that. So the first is the what is the resonance frequency of a proton in magnetic field of 14.1 Tesla. Now first remember that what is the formula. 15.1 A. So the resonance frequency, you remember that delta E is actually H nu L, right? Now which is actually you can write it in two times, gamma H cut beta Z, and you can also write it in terms of nuclear G factor, your nuclear magnetron, and then obviously your magnetic field along the z axis. So, so the resonance frequency will be, suppose here nu L is actually going to be nuclear G factor, your nuclear magneton, your magnetic field along the z axis by your suppose H, right? So what is the Gn for a proton? For that we have to go to the Atkins book, I guess. Let's go. Atkins book is here. Atkins book is here. Let us see. Yeah. So for proton, the G factor is 5.586. Okay. Okay. Let us go there and try to solve that. So 5.585. And what is the mu n or the Bohr magnetron for that? For that also I have to go again to check what is the exact value. Um, Actually, it's not here. Let us, we can also try to find it out. What is nuclear G factor, right? Or no? Nuclear magnetron of proton, right? In Wikipedia, it is given the SI unit 5.050 into 10 to the power minus 27 Joule Tesla inverse. 5.050. Okay, let us take that. 5.050 into 10 to the power minus 27, right? Joule Tesla inverse, and then your Magnetic field is given 14.1 Tesla, right? And then our Planck constant is there, right? 6.626 into 10 to the power minus 34 joule into second. So joule will cut, Tesla inverse Tesla will cut. Now this second will go to second inverse, right? Or hertz. So let me calculate and give you the value what will come. 5.585 into 5.050 into 10 to the power minus 27 into 14.1 divided by 6.626 divided by 10 to the power minus 34 by 10 to the power 6. That will come around 600 into 10 to the power 6, which is actually 600 megahertz. Okay, so let us also solve the second problem. Second problem will be in line with that, right? 15.1b. Same question for 19a. So the first thing is to remember that delta E is not going to be changed. Okay, delta E will be same. That is h nu l, and it will let us equate that to Gn, nuclear magnetron, and this thing. So your Larmor frequency will be, or the resonance frequency will be uh, same. We have to understand what is the G value for 19F. So let us go and check if that is there in the book. For 19F it is not there, so we have to search it here also. So if it is there for the magneton of 19F, G factor is given 5.253. Okay. Is it, no, this is it for 19F? Okay, this is given. Um, is it given in this portion? Now 5.25 is correct. 5.257. Okay. Into your mu n was there, right, in Wikipedia. Let us take that value. Is it correct? I think I'm making one mistake. The nuclear magnetron is same for all, right? Because it is a mass of a proton. So nuclear magneton will be same for all. So this is a very bad mistake what I have done. I hope you understand what I am trying to say. So the nuclear magnetron for sorry, not this. Nuclear magnetron for proton or nuclear magneton for 19F or 13C, all is same, right? That is 5.050 into 10 to the power minus 27 joule Tesla inverse. Why? It is actually equals to EH by 4m pi, or you can say 2m mass of proton. Mass of proton is same for all, right? So it will be same for all. So let us also multiply this 0.050 into 10 to the power minus 27 joule Tesla inverse into here the BZ is changed, right? It is 16.2 right now. 16.2 Tesla divided by 6.626 into 10 to the power minus 20 minus 34 joule second. Joule will cut, Tesla inverse, Tesla will cut. Let us see what answer will come. I'm just calculating it here. So all the things will remain the same, just 5.257 into 5.050 into 10 to the power minus 27 into 16.2 divided by 6.626 divided by 10 to the power minus 34 divided by 10 to the power 6. It is actually coming as 649 into 10 to the power 6 hertz. It is actually, you can say, 649 megahertz. There are some values after the decimals which I am not taking. It was there, but it is better you can take it also. Okay. Now let us go to the next question, that is 15.2a. So 33 sulfur has a nuclear spin of 3 by 2 and a nuclear G factor is given, that Gn is given, that 0.4289. So now we have to calculate the energies of the nuclear spin states in a magnetic field of 7.5 days. So I hope you remember the delta is coming. You remember that E of individual mi will be actually was minus Gn nuclear G factor, then your this, right, and then mh cut and your bz. Okay, bz is the magnetic field along the z axis. Okay, now this is the main for each spin state, this is the energy. Okay, now let us just quickly do this thing. Minus G factor is given 0.4289 into mu n, we already know 5.05 into 10 to the power minus 27 joule Tesla inverse. M I value we don't know yet, we will know. Then there is 6.626 into 10 to the power minus 34 joule second, right? Am I writing it correctly? I think I am not writing it correctly. Each cut won't be here. I think yes. I think that gyromagnetic ratio into each cut is actually equals to your Gn Bohr magneton. This is another formula you should remember. So I will remove this. Okay. And I will remove it from here also. Now your B's mi value we don't know yet. We know 7.5 Tesla is there. Okay, into mi. So let us see how much we are getting from calculation. Wait, let me check if the Google meeting is running or not. Oh my god. Okay, we are back. Yes, it is recording. Okay, I'll give you the values after calculation. Okay, 0.4289 into 5.05 into 10 to the power minus 27 into 7.5. Right? That is actually minus 1.6245 into 10 to the power minus 26 AMI. Actually, the unit you can understand, unit will come in joules, right? AMI has no unit. So for 33 sulfur, you can see the nuclear spin is 3 by 2. So when it will be in a magnetic, suppose when the magnetic field is not there, then is all the spin state are degenerate, right? Now when the magnetic field is removed, then you can see that the spin states are going to be, there are four magnetic nuclear spins, right? So depending on the energy I will give you, so after the magnetic field there will be four such Gaurav, change. um, First change, first block the pathway and change the yeah, sample, means that check the reference with Komari. And for 530 we don't have to do much, right? Just change the wavelength. You don't have to remove means go to a lot. Okay. Now for um, uh, see, for now for 3 by 2 we'll get into, for see minus 3 by 2 will have positive energy, right? So minus 3 by 2 will be stabilized. So this is for minus 3 by 2. This is for minus half. This will be for plus half. And this will be for plus 3 by 2. Okay. Now what will be the energies? So we can calculate directly, right? That for this it is, for this the energy is 8.12 into 10 to the power minus 27 joule, and this will be negative, right? This is for plus and this is 8.12 into 10 to the power uh, actually this is plus, this is minus, right? This is plus mi and this is minus mi, minus minus will be plus, right? It is minus 27 joules, right? And it will be 2.44 minus 2.44 into 10 to the power minus 26 joule, and it will be plus 2.44 into 10 to the power minus 26 joule. Gora, run in AC9, greater neutral density value. Nine. Okay. Okay. Sorry, I was actually asking my lab mate to actually run an experiment for me. An experiment is going on. Okay, no issues. Uh, Now, so these are the energies are going to be for each spin states. Now, same thing we are going to do for the 15-2B. Okay, let us do that. So, acha, let me first copy the questions and then we'll come. Just quickly copy the questions so that we can solve it here. Okay. Now we'll solve 15.2B. Okay. So it is said that 14N has a nuclear spin of 1. So you can understand when the magnetic field will be given, it will split into three, right? One will be one will come here, one will be here, and one will come here. So it will be minus one will be here, zero will be here, and plus one will be here. These are the three nuclear spin state that is possible. Now, what is the energy of each nuclear spin states? I told you the G factor is different, so it is actually minus Gn, right? Mu n, the nuclear magnetron, AMI, and your magnetic field along this. So for this, let us calculate what will be the thing. Um, it is actually minus 0.404 into, again we know this, 5.050 into 10 to the power minus 27 joule Tesla inverse. AMI value will put later, but we know the Tesla in magnetic field and AMI, right? So let us calculate this, how much it is coming. Actually, I'll just change it. Okay, minus 0.404 into 5.05 into 10 to the power minus 27 into 11.5 Tesla, right? That is actually giving us minus 2.35 into 10 to the power minus 26 AMI Tesla. See, earlier we got a value of 1.624 and now we got almost double because uh, the magnetic field has changed and the Gn value is quite low for. Well, it's similar to the 33 years, but it's a little less. So easy. So it will be even easy for now. You don't have to multiply by half or minus one. So you can see the here the energy will be 2.35 into 10 to the power minus 26 Tesla for this, right? Here you get 0 joule. Actually, your unit is going to be joule. I'm making it a mistake because your joule Tesla and this Tesla inverse will cut and joule will remain, and it will be minus 2.35 into 10 to the power minus 26 joules. Okay, okay. So 15.2b is also done. So let us solve 15.3. Okay. The first question is calculate the frequency of separation of the nuclear spin levels in 13C nucleus in a magnetic field of 14.4 Tesla given that magnetogyro ratio is 6.73 into 10 to the power 7 Tesla inverse second zero. See, now instead of Gn or nuclear magneton, gamma, that magnetogyric ratio is also given. So you also know this formula, right? Same thing I am reading. So earlier we are using this, right? Now we are going to use this gamma h cut beta z, right? So this is h nu l is gamma h cut beta z, right? So nu l is actually gamma beta z bz by 2 pi. So your gamma is given, which is acha, our here is calling Google Meet. Stay in the call. Now let us put the values. 6.73 into 10 to the power 7 Tesla inverse, second inverse. Bz value is also given 14.4 Tesla divided by 2 into 3.14, right? Tesla this part. Now let us see what is going to the value. 6.73 into 10 to the power 7 into 14.4 divided by 2 divided by 3.14. 2 point, uh, which is going to give us a value of 10 to the power, if I do 154.3 megahertz. Okay, so this is the value we are going to get. I hope you are understanding this. This is a very easy problem actually. Now let us solve 15.3b. To calculate the frequency of separation of the nucleus spin levels of a 14N nucleus with a magnetic field is given. Again the magnetochiral ratio is there. So you'll use the same formula. The new L is gamma Bz by 2 pi. Now the nucleus has changed. So it is the same, but the value of the magnetochiral ratio has changed. In some book it is given gyromagnetic ratio, some yes it is given uh, magnetochiral ratio. Both are same actually. Now into 15.4 Tesla divided by 2 into 3.14. 15.4 is the thing, and the answer is coming to be 47.2, 47.33 megahertz. Okay, the answer is coming in hertz, but in 10 to the power 6 order, so it is changing. Okay, so let us solve 15.4a. In which of the following system uh, is the energy level of separation largest? A, that is 600 megahertz NMR spectrometer for a proton and deuterium in the same spectrometer. Now, as you can see, the energy separation is delta E, right? Which is equals to Gn, your nuclear G factor, your nuclear magnetron, and then the magnetic field, right? Right. So if you are using the same spectrophotometer 600 megahertz, then your Bz is also same, magnetic field is also same, right? We can think like that. So in that case, your delta is going to be a factor of, it will depend on varies as your nuclear G factor. But the nuclear G factor of a proton and a deuterium is different. Okay, so for a proton, the nuclear G factor is, so delta E for 1H will be divided by delta E of deuterium, or 2H, you can say 2H. Deuterium is a nucleus of a deuterium. Okay, so this is Gn of 1H, Gn of 2H, right? So let us check what is the value. I think it is given here. For a proton it is 5.585 what we are taking, and for it is 0.857. Okay, 857. So this is 5.585, that is 0.857, which is obviously greater than 1, right? So your separation of a proton 1 inch will be greater than your separation in your deuteron. Okay, so this is how we will solve this. Just wait for 2 minutes. Okay, so is our Google Meet is running? Let me check once if someone is there. Uh, no. Okay. So I'm very sorry that I'm keeping one gap in between because I'm doing one experiment, very important experiment. So I'm just going and checking that and asking my friend to help me, lab mates. So please uh, excuse me on that thing. Okay, thank you. Uh, so now I think 15.4a is also done. So let us go back to other questions. What I have, let's see. So let me save up to this so that I can share this thing with you later. I think we have the next set of question here. Okay. So there are a few more questions here. Let us do that. So we need to calculate. The first question says we need to calculate the energy difference between the lowest and the highest nuclear spin state of a 14N nucleus in a 15 Tesla magnetic field. So that's not a big deal, right? For let us see how we have done just earlier, right? That how the in a magnetic field how it will split for a 14N. 14N has a uh, nuclear spin value of 1, right? So it will just split into 3 nucleus with plus 1, 0, minus 1, right? So here no B0 or BZ, here presence of BZ. Okay, here the thing is degenerate, here the degeneration is lost. Okay, now we know the formula. Ej equals to Ej not EMI is equals to minus Gn Bohr magnetron, your AMI and your BZ, right? So AMI, so for minus 1 it will be obviously Zn mu n Bz, and E plus 1 it will be Zn minus Zn, your nuclear magneton, and then your magnetic field. So the gap between plus 1 to minus 1 or minus 1 to plus 1, whatever you are trying to write, it will be something E minus 1 minus E plus 1, right? Which will be actually 2 Gn mu n Bz. So let us see how much it is. 2 into nuclear Z factor is given. Nuclear Z factor of 49 earlier is given. See 0.404, 0.404 for 15.2b question. 0.404 Tesla. Actually, a G factor doesn't have any unit. Now this your nuclear magneton has unit 10 to the power minus 27 joule Tesla inverse, and then your Bz value is there, right? Bz value is given, that is 15 Tesla, right? So Tesla we got, and you, in joule you will have your answer. So let us see how much it is coming. 2 into 0.404 into 5.05 into 10 to the power uh, minus 27 into 15 Tesla, which is actually, the gap is actually 6.12 into 10 to the power minus 26 joules. So you can see that the energy gap is very low, right? Even lesser than the rotational levels, right? That is why you need a radio frequency or radio pulse, right? For this case. Okay. So similar way we will try to solve 15.5b. What is the question? Calculate the magnetic field required to satisfy the resonance condition for unshielded protons in a 150 megahertz radio frequency. Okay, that is actually a different kind of question. So the magnetic field, we need to calculate the magnetic field needed to satisfy the resonance condition in a 150 megahertz radio frequency, but for which nucleus it is, a proton it is given, unshielded protons, right? So okay, so what we need know, that your nu L is actually, we can write it h nu L or the delta E, actually Gn mu n Bz, right? So your nu L is given, your this thing we already know from the previous question, and we need to calculate Bz, right? So magnetic field is h nu L by Gn into mu L, right? So h we know 6 Planck constant 6.626 into 10 to the power minus 34 joule second. Then your nu will come, nu is 150 megahertz, 150 into 10 to the power 6 second inverse. Then your G factor we know, right? For proton 5.585, which has no unit, and then the mu 5 point nuclear magneton, which will have some unit, the value of which is 5.05 into 10 to the power minus 27 joule Tesla inverse. So second will cut, joule cut, Tesla inverse will become Tesla, right? So let us find out how much Bz is there. 6.626 into 10 to the power minus 34 into 150 into 10 to the power 6, right, divided by 5.585 divided by 5.05 divided by 10 to the power minus 27, that is 3.53.54 Tesla. This is the answer. Okay, I hope you are getting the point. These are fairly easy points. So here we are trying to just use the formula and see what kind of problems may come, right? So okay, so let us go to 15.6a. Use the table 15.2 to predict the magnetic field at which the 1H, 2H, the deuterium, and 13C come into resonance at 250 megahertz and 500 megahertz. So let us first, so the formula will be same, right? The formula will be Bz is equal to H mu L by Gn mu n, right? Now for, let us start with 1H, and 1 is 250 megahertz. So it will be same, 6.6 to Bz will be 6.626 into 10 to the power minus 34 joule second into, now instead of previous 250 into 10 to the power 6 second inverse, as we are using proton NMR, 5.585 into 5.05 into 10 to the power minus 27 joule Tesla inverse. So let us see how much we will get. I'll just put the value of, I'll just change the magnetic field, the frequency, lambda frequency, to get the same answer. So I think we'll get something around 5.87 Tesla. Okay, for 250 megahertz. Now for 500 megahertz, I'll not write the whole thing, I'll just write the answer. So I hope you understand. I am going to repeat the same thing like this. Into 500 megahertz. So I think it will just double down, right? 11.75. Okay. So now for, let us go to the same for the deuteron. So I'll just copy paste the questions, right? Just copy paste the questions here. So we are currently solving 15.6a and B part for deuterium, right? First is 250 megahertz, then we'll go for 500 megahertz. So for 250 megahertz, it is now 6.626 into 10 to the power minus 34 joule second into 250 into 10 to the power 6 second inverse. And then for deuteron, the value I told you, let us check, I just forgot it. The value is for the G factor, I think is, where is the value? For which question did we use that? Um, Last 15.4a, right? 0.857. 0.857 into the G factor I looked for is like this. So here it is again 250 instead of 5.857. So actually you are going to see now you will require a much bigger uh, magnetic field because it has less, right? So you are going to see 38.28 Tesla. Okay, and obviously for this it will double down, right? 76.55 Tesla. Now for C part, which is for 13C, 250 megahertz, and then 500 megahertz. So the G factor is for this. The G factor is for 13C. G factor is 1.404. Okay. So it will be 6.626 into 10 to the power minus 34 joule second into 250 into 10 to the power 6 second inverse 1.404 into 5.05 into 10 to the power minus 27 joule Tesla inverse, that is going to give us 23.36 Tesla. Okay, and for it is going to double down, right? 46.73. Okay. Now comes the question 15.6b. So we'll also solve this because it will be a good problem to know the nuclear G factor for 14N, 19N and 31P, right? I'll provide. Okay. So let us come back to the problem what we are solving. Uh, okay. So we'll try to solve for the rest of the uh, nuclear. One is 14N. For it we'll solve 250 megahertz, 300 megahertz and 750 megahertz. For 14N the GN factor is actually 14N the GN factor is for 0.404, right? We took it earlier. So it is 6.626 into 10 to the power minus 34 joule second into 300 10 to the power 6 second inverse by 0.404 into 5.05 into 10 to the power minus 27 joule Tesla inverse, which is equals to which is equals to 0.404 97.43 Tesla. Now for 750 it will be, I'll just replace the alarm frequency value, it will be around 243.58 Tesla. Okay. Now for the next nuclei is 19F, right? So for 19F the nuclear G factor is, we already worked on this, right? 5.255. 5.255. So at 300 megahertz it will be, I'll just write for this, I will not write for 750, right? 6.626 into 10 to the power minus 34 joule second into 300 into 10 to the power 6 second inverse divided by 5.255 into 5.05 into 10 to the power minus 27 joule Tesla inverse, which is will be actually 0.255, 7.49 Tesla, and for 750 I'll just replace the value of normal frequency again. It will be something around, it will not exactly double but more than double, 18.73 Tesla, because it is not 600 megahertz right now, right? It is 750. So for C it is 31p, right? And if GN for this is, GN for this is 2.261. Okay, 2.31 is 2.261. So for 300 megahertz it will be something, I'll just give you the answer directly. Okay, so for 300 it is um, 2.261, which is 17.41 Tesla. For 750 it is 43.52. Okay. So that's how you solve question number 15.6 A and B, and then let us go to 15.7A, right? Okay, what does the question say? Calculate the relative population differences delta n by n for protons in fields of different magnetic field at temperature is given 25.75 degrees Celsius. So again here we will use Boltzmann distribution, right? Function. So that is your n uh, beta by n alpha is actually going, because beta will have higher energy, right? Will be dependent on exponential, or you can say equals to also, is to minus delta E by kBt, right? Now you can see here the delta is very less actually, right? So this is your delta n is actually your n alpha, uh, alpha is your plus spin, right? And beta is negative. So actually your alpha minus, actually alpha minus n beta, right? And n is total number actually, so it is n alpha plus n beta. So let's see what is delta n by n is actually. So n alpha minus n beta, the number of alpha, number of beta, okay? N alpha plus n beta. So if we take common outside n alpha, 1 minus n beta by n alpha, right? By n alpha common, 1 plus n beta by n alpha. Okay. So you are going to get 1 minus n beta by n alpha and 1 minus n plus n beta by n alpha, which is actually, if see, it is 1 minus x e to the power minus delta E by kBt by 1 plus e to the power minus delta E by kBt. So as I'll write some question here, as delta E is very less than kBt, thermal energy, as you have understood. So we can write exponential e to the power minus delta E by kBt to be 1 minus delta E by kBt. So you're actually uh, delta n by n is going to be 1 minus 1 minus delta E by kBt by 1 plus 1 minus delta E by kBt. So as I told you that delta E is very less than delta E kBt, so I'll just in numerator we will use delta E by kBt, and in here we will use only 1 plus 1, and this will be tends to 0. We will just take it as, because it is very less than 1, right? So ultimately it is delta E by 2 kBt. Now you can write it in terms of Gn, your mu n Bg by kBt, or you can also write it in your magneto-gyric ratio, this formula by kBt. Okay. So what does, so let us copy paste the question once so that we can see what we are trying to do. Copy paste it here. So we are solving this problem, right? So let us see for 30 Tesla what it is. So let us first calculate what is for proton, what is Gn mu n by kBt, T being 25 degrees Celsius, okay, means 298 Kelvin. Let us see that. We know this is 5.585 into 5.05 into 10 to the power minus 27 joule Tesla inverse. Kb, you know, Boltzmann constant 1.38 into 10 to the minus 23 joule Kelvin inverse into 298 Kelvin. Okay, Kelvin cut, joule cut, Tesla inverse will be there. So I will come back to this, but let me give you the value. So the value will be 5.585 into 10 to the power minus 27 divided by 1.38 divided by 10 to the power minus 23. Okay, this is coming as a value of 0.0000405, something like this. I am taking this much decimals because you will understand. So for delta n by n for proton at 0.3 Tesla, it will be 0.000405 into 3, okay, point 0.3. So it will be, so this is Tesla inverse into Tesla 0.00012, something like this. Okay, now that B is equal to 0.3 Tesla. Now delta n by n at BCA is equal to 1.5 Tesla. How much it will be? 0.000405 Tesla inverse into 1.5 Tesla, which is 0.00061 actually. No AD it will be there. Okay. Now delta n by n at BZ 10 Tesla. Same, right? I'll directly write 0.00405, something like that, right? Okay. Okay. So the same thing can be done for the, say, this question, right? 15.7b, where we know that Gn, now we know 1.404 for 13c, right? So for this factor, if we can get this Gn into mu n by kBt, here also we use 298 Kelvin. Gn will just change it 1.404, which will give us 0.00102 Tesla inverse. Okay. Now In BZ value of 0.5 Tesla, it will be We just multiply this thing with 0.5, right? Tesla inverse and Tesla. Actually, one more zero will be here. So you get something around 0.087 into 10 to the power minus 5. Okay. See, for this 13C, the it is even less, or almost you can see 0.5. Actually, it is more, right? Why it is more? Because Gn value is less. So the delta n by n value is lesser than that of the proton. Obviously, the Bz values are different. You can't really compare. That's why. So it will be 0.0000102 into 2.5. 0.0002543, which is actually 1, 2, 3, 4, 5, 5.43 into 10 to the power minus 5, right? You can write it in any term, any kind of this. You just need to solve it. Very easy problem, right? 15.5 Tesla. You just need to know the proper numerical formula and you will be able to solve it very easily. 15.5. This you are going to get 1, 2, 3, 4, 5. Actually 157.695 into 10 to the power minus 5 this minus 5. Right? So if we write, we can write this thing is also in terms of that 12 into something was there extra, right? Into 10 to the minus 5. Here it was 61 into 10 to the minus 5. Here it is 405 into 10 to the power minus 5. Some more decimal points are there, but you can write it also in this kind of way. Okay. Now let us discuss 15.8. So the question is the fast generally available NMR spectrometers operated at a frequency of 60 megahertz. Today it is not uncommon to use a spectrometer that operates at 800 megahertz. So what will be the relative population differences in 13C spin states in these two spectrometers at 25 degrees centigrade? So from the previous question you understand that your delta n is actually it is something like uh, delta n by n is your from this part, right? Delta n by n and delta e by 2 kbt, or you can write it, I'll write this part, delta e by 2 kbt. But one most important thing is that delta e is very less than kbt, right? This is the important thing, so that we are getting this. So you can understand that your delta n is actually dependent on delta e, and that is your h nu male, or you can say nu male, right? So delta n is actually varies as nu male. So delta n at 60 megahertz by delta n, sorry, 800 megahertz by delta n at 60 megahertz, it will be around 800. You can write it like this, right? which is coming as 13.33 some value. Okay, it is coming like that. So you can see that the relative populence difference in these spectrometers are there, right? Not there. Delta N, it will be not very high. So that's all you can say from this question, right? So delta N, the population difference of alpha and beta spin in in 600 megahertz, 60 megahertz was less than that of the 80 megahertz. You can say like this also. Okay. Now we will go to the next set of questions. Right. Let's save this part and check if the Google Meet is running. Okay, the recording is also going on. Okay, so we have a few more questions. 15.9a. The question says the chemical shift of the CH3 protons in acetaldehyde or ethanol is delta 2 point. So two chemical shift values are there, 2.20, and that of aldehyde proton, CHO proton, is 980. So what is the difference in local magnetic field between the two regions of the molecule when the applied magnetic field is 1.5 Tesla and another is 10 times 15 Tesla? So you remember, right, that your actually your B effective due to the shielding is actually your 1 minus shielding constant into your B0, right? Okay. So this is actually your, that's it, and your chemical shift delta is actually nu minus nu 0 by nu 0 into 10 to the power 6. This in ppm it will come, right? Or you can also write in this term that your delta is uh, so effectively your um nu L actually is, so from this actually you can write it is 1 minus sigma beta gamma by 2 pi, right, minus 1 minus sigma 0 beta sigma by 2 pi by 1 minus sigma 0 beta sigma by 2 pi. Now this will cancel out, 1 minus sigma you will get minus 1 minus sigma naught by 1 minus sigma naught, which will give you sigma naught minus sigma by 1 minus sigma naught, which is actually equivalent to sigma naught minus sigma, because this is very less than 1. Okay, you can write it like that. So what you are actually seeing, I am missing this part, 10 to the power 6, 10 to the power 6 into 10 to the power 6. Okay, so actually this change in delta actually will give you, suppose you, if you want to see the what is the difference in the local magnetic field, so your delta B effective actually is um, you can say 1 minus sigma of CH3 proton minus 1 minus sigma for your aldehyde proton. So, so you can tell me, right, your aldehyde proton is, you can see it is 9.80, means much more deshielded. So aldehyde proton shielding constant is very less. But for CH3, the methyl proton is at 2.20, that is much more shielded, right? So the shielding constant is much more for this. So 1 minus sigma will be lesser for this, B effective. So I'll get back to that. 1 minus sigma. I think B0 is the same, right? Okay. So I can write it in terms of so actually I can take the bracket after this, right? So 1 minus 1, so effectively sigma CHO minus sigma CH3 into B. And I can also write it in this fashion, right? Sigma 0 minus sigma CH3 minus sigma 0 minus sigma CHO, right? V naught. So from here we understand that your sigma 0 minus sigma is actually delta into 10 to the power minus 6. So for this CH3, what we are going to get? Change कर दो. How much? What is the delay right now? Gaurav? Huh? So change it to 5. No. 540 is the yeah. And what is the delay? So change it to 550. Now, just block the pathway and then change, huh? So the sample recovery is much more. Okay. So sigma 0 minus sigma CH3. So now we know this will come for delta CH3, right, into 10 to the power minus 6 minus this will come for delta CHO into 10 to the power minus 6, and magnetic field, given magnetic field is the same, right? So it is actually your delta CH3 minus delta CHO. We'll take a mod of that modulus, right, into V naught, or else minus value won't matter actually. Here we'll take it as a modulus in modulus form. So it is 2.20 minus 9.8 into 10 to the power minus 6 and into B. Bz value for fast, it is 1.5 Tesla, so we'll write it like that. Delta B effective is actually going to be, I will write it 2.20 minus 9.8 into 10 to the power minus 6 into 1.5, which is actually very less. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1.14 into 10 to the power minus 5. Okay, in Tesla, because this has no unit this much and this has a unit of Tesla, right? Okay. And at 15 Tesla obviously it will be 10 times, right? 15 Tesla, it will be delta B effective will be 1.14 into 10 to the power minus 4 Tesla. Okay, so okay, now let us solve the same for I think something is different in the next question. No, we'll try, still we'll try to solve that. Okay, just go outside and copy it. Acha, we don't have any more blank column. Okay, so we'll just, I think we'll need just two maybe. We copy the question. Okay, that was tough. So the question is as like the previous one. So we already know that what is your going to be your delta. So I'll just quickly write the formula, right? 15.9b, what we got from 15.9m, that delta B effective is going to be a modulus of some two deltas are here. For here you have a chemical shift for diethyl ether, two kind of protons are there, methyl and ethyl. So not ethyl, CH2. So for that you will need CH3 minus CH2 and into 10 to the power minus 6 into your B Z, right? Whatever you are using effective B0 you can also write. So here it is 1.16 minus 3.36 modulus of that. It is going fine, right? Okay, thank you. 2.20 into 10 to the power minus 6 into B0. So which is actually for the first it will be, we'll do it for 1.9 Tesla and then we'll go for 16.5 Tesla. So it will be 2.2 into 10 to the power minus 6 into 1.9, right? Which is actually 1, 2, 3, 4, 5, 6. And it is even more. 4.18 into 10 to the power 6 minus 6 Tesla. And there it will be 16.5. 1, 2, 3, 4, 5. 3.63 into 10 to the power minus 5 actually here. Okay? Okay. Now the question is that 15.8a. Sketch the appearances of the 1H spectrum of acetaldehyde ethanol using J value of 2.9 Hz and the data in the exercise 15.9a in the spectrometer operating at 250 megahertz and 550 megahertz. So we already know that delta value we know. So this I need to copy it again, I guess. I'll just then go to another page. I'll just copy the whole thing. So I'll just keep the required part only. Now the question is, sketch the appearance of 1-inch NMR spectrum of acetaldehyde using J value of 2.90 Hz and the data given in 15.9. So from 15.9, what is given? The delta of 2.20 and 9.8. So what is the actually the difference between them? That uh, appearance you can easily think, right? So acetaldehyde, it is given that, so it is one proton, but the coupling will be like CH3 is there, AX kind of system, right? So here AX3 kind of system, right? So it will be splitted into 1 is to uh, how much? 1 is to 2 is to 1 is to 3 is to 3 is to 1, right? So 3 is to 1. How to remember that? First it was 1, then it will become splitted by 2, right? The gap will be J. Now it will again split into 2, right? And then again uh, it will so it will again J is the coupling constant here. Now it again it will split into 2. For this it will have another 2, 1 is to 3, because there are 2 are there, right? 1 is to 2 is to 1, right? 1 is to 2 is to 1. Now here it is 1 is to 3, and because 1 from here and 2 from here, and here it will 1. So it is actually 1 is to 3 is to 3 is to 1. So for acetaldehyde, the aldehyde proton will split it like this, and your methyl protons are going to be split it like uh, in a doublet, right? And the J is given 2.9 Hz, and here also 2.9 Hz, 2.9 Hz, 2.9. One more important thing is that the if you do a integration, so here it will get only one proton, so the intensity will be very less. Intensity or area under the uh, curve, it will be something x, and here it will have 3x, right? Because there are 3 protons are there. So this is another important thing you need to understand. Now for 250 megahertz and 500 megahertz, what is going to be the relative change? The J value won't change. The delta lambda will delta nu will change, but you will see that see the delta nu is nu for CH3 minus nu of CHO, which is again we can write in terms of nu of CH3 minus nu 0 minus nu CHO minus nu 0, right? You can write it like that, and even uh, like that. And if you take nu 0 here, you don't have to take this. This is actually your nu 0 into what? 10 to the power delta nu by nu. This is your delta actually, right? Am I making sense? What I'm trying to say? And here 10 to the power into 10 to the power 6 was there, so 10 to the power minus 6 will come here. So this is equals to your nu 0 into delta into 10 to the power minus 6. So actually your delta nu is nu 0 into delta into 10 to the power 6 minus 6. So for a 250 megahertz, delta nu is 50 into 10 to the power 6 into delta value is, you know, right? We'll have to take a actually we have to take a difference in delta, right? And 9.80 minus 2.2 into 10 to the power minus 6 is this will cut. So 250 into 250 into 9.8 minus 2.2. So it will be something around 1.9 kilohertz, and for 500 megahertz 3.8 kilohertz. Okay. But the thing is that your shift, chemical shift in in ppm scale or universal scale, delta scale, actually will not change with spectrometer and new well. Huh? That won't change because eventually you are going to divide it, because your delta is actually nu minus nu naught by nu naught is there, right? So eventually you are dividing it by this, so it will be normalized. Let me place my cursor into actually 10 to the minus 6. Okay, so it will get normalized. So what will happen if you increase the if you increase the Larmor frequency or the spectrophotometer frequency, the first order spectrum will be much more resolved. So if it was a multiplate, so you may see a proper splitting, what coupling is happening. So the coupling will not change and the delta will not change, but what will change? The spectra will be much more resolved if you increase the new L. Okay. So with that, I think we don't have any more problem to solve, numerical problems. So, and it is also 8:15. Anyway, I took some uh, I took some time in between. So let us in 15 minutes quickly we go through the whatever overall course matter we had, right? We can do that, right? Let us do that. So let us come here and let us go to the week 0. What was there? So week 0, nothing was there. So week 1 we had, so I'll go here. I know you have an exam very soon. So on week one, there was lectures, 5 lectures on frequency domain spectroscopy. Then where you have introduced to the Fourier transformation, right? Fourier transformation in frequency domain, how time domain to frequency domain is the natural one what we use in spectrophotometer in UV visible absorption spectrophotometer or in spectropluidimeter, that is the frequency domain measurements. Now we have understood the schematics of the instruments in for absorbance as well as the emission spectrophotometer, and we understood the what is the signal to noise ratio, right? The more will be the signal by to noise ratio, I think it will have a some square root of n, right? Something like that. So more will be the signal, less will be the SN ratio, S by N. And we have understood also the various factors in the instrumentation slits, monochromator, these all the things we have learned. Then we went to the time domain spectroscopy, which is actually then how to convert our time domain to frequency domain or frequency domain to time domain using Fourier transformation. And then in week two, we have talked about, we have started talking about the rigid rotor model of the diatomic molecules. What actually we have started the rotational spectroscopy there, and you can also say microwave spectroscopy. And we have understood the selection rules for that. What are the main condition to be microwave activity? It was that it should have a permanent dipole moment, right? So homonuclear linear molecule, diatomic molecule actually are not microwave active. They are microwave inactive. So you have to have a permanent dipole moment to have a transition moment, non-zero transition moment integral, and that's why your you should have a microspectroscopy to be non-zero permanent dipole moment. Now next we have in the next week after that we have discussed the simple harmonic oscillator, means the IR spectroscopy or the vibrational spectroscopy, where the vibrational spectroscopy means the vibronic levels are much more has some difference than the rotational energy than the rotational levels, right? So each vibrational levels contains the rotational levels, right? And then we have discussed high resolution IR spectra, what is anharmonicity, and then we discussed the Raman effect. Raman effect is nothing but the scattering of that light. We have discussed Stokes shift and anti-Stokes shift, and we have also discussed different selection rule for that, right? For and we have also discussed the population, how the population is going to be in different rotational level and different vibrational levels. We have seen that in room temperature, the all the most of the rotational levels are almost the population all populated, but in case of the vibrational levels, we have seen that only the uh, mu zero or the V0, you can say the ground vibrational state was highly populated than the new one. So that's where the concept of fundamental, fast overtone, second overtone, these things came. Now there is something like in anharmonicity we have discussed what will be the anharmonic oscillator is there, and then we went to the Raman spectroscopy. In Raman spectroscopy we have understood there are two kind of Raman things, rotational Raman and vibrational Raman, right? Where we have discussed about the polarizability factors, right? Not and which are IR for a centrosymmetric molecule. We have also mutual exclusion principle. We have studied that say if a centrosymmetric molecule is a some frequency, some normal mode of vibration is IR active, then it will be Raman inactive, and if it is Raman inactive, sorry Raman active, then it will be IR inactive. So those are the things we have learned. And then in week four, we went to, I think, to the semi-classical treatment of the radiation and matter. We have discussed that the perturbation theory, how the transition moment integral, what is actually the transition moment integral is, and why it can cause the. We have also I think learned Fermi golden rule there, and how the natural line width will come. And we have also learned the Einstein treatment of two level system, right? And then so it was a very important week 4. Now we went to the laser systems, where the population inversion may takes place. So level systems like and lasers basic and applications of laser spectroscopy, we have discussed that we have applications very much, and in ultrafast dynamics how lasers are used. Now snapshot of one breaking, these are experiments by Nibaring and Ahmed Jewel. I think Ahmed Jewel's experiments we have discussed. In week 6 also we have discussed that. Week 6 we went to Raman effect. Um, Ramon, I think in this week we have learned actually we learned what is Raman effect, what are the anti-Stokes Raman effect, what are Stokes Raman thing, right? And now then we went to the symmetry part. Why the symmetry was necessary? Symmetry was necessary to understand the spectroscopy of polyatomic molecule beyond the homonuclear diatomic molecule. So there we have learned how the symmetry transfer, what symmetry operations or symmetry elements are, and what is transformation matrices are, and what are reducible and irreducible representation. How we can provide one our symmetry as a symmetry operation in what are the relationship there. Then we have understood the point groups, character tables, and how the character group of each point group, how we can have the irreducible representation, and what are the in character table, what are the nomenclature of the each irreducible representation. There we have taught or learned about great orthogonality theorem, right? Relationship between each irreducible representations that came up that time. And in week 7 we have done that, and week 8 we went to how we can use different atoms or different wave function as a basis, and how symmetry of atomic and molecular orbital we have discussed, and we have tried to understand what are the normal modes of vibrations are, right? And how many normal modes. So it will depends on 3n or degree of freedoms, right? How many normal mode. So normal modes of freedom will be, vibration modes of freedom will be, and the total modes of freedom will be 3n, right? N is the your total number of atoms in a molecule, and it will consist 3 translational motions and 2 rotational motion if it is a linear molecule. If it is not a linear molecule, then it will have 3 rotational freedom. So for the vibrational motion, it will have 3n minus 5 in case of a linear molecule, and 3n minus 6 in case of a non-linear molecule. The degree of the total modes of normal modes, right? Vibrational normal modes. And then we have understood how the symmetry of, what will be the symmetry of those normal modes in details, and also the shortcut methods, right? From the character, using the character tables and the group multiplicity multiplication, we have understood that. And what is, which normal mode is IR active, which are Raman active, right? Then we went to IR and Raman activity electronic spectroscopy, right? This electronic, here we have first we have assumed that von Oppenheimer approximation is valid, where the electronic levels, vibrational levels, or the rotational levels doesn't really talk to each other. But then we have also discussed some cases where the von Oppenheimer approximation is uh, bricked. Okay. And then in week 10, what did we learn? Week 10, we have learned the rotational fine structure in a electronic spectra. What are the symmetry of electronic state? We have discussed the benzene. I remember we have discussed about the of benzene, and I think for oxygen. It was very important. I hope you go through the parts again and get a quick recapitulation of that part. And in week 11, we went to a totally different thing, that is NMR spectroscopy, nuclear spin. So there, first in lecture 55, we have discussed the basics of NMR spectroscopy, and then how NMR spectra measurements were done. And actually the things is written wrong here actually. Here actually we learned how what is spin coupling, right? We learned what are the spin coupling in AX system, and the coupling is actually a perturbation. Using a perturbation we learned what will be the change in the energy states when there is no coupling and when there will be coupling. And then actually we have learned about spin lattice relaxation and spin relaxation. With that, we have ended our molecular spectroscopy course. I hope you got a gist of this. I know I was very quick. I hope you are going to appear for the many of you are going to appear for the exam, and you are going to get very good marks, right? I hope you are going to get very good marks there, and I hope it was a learning experience for you as well as for me. It was really a learning experience for me, and I hope you perform well in your exam. If you have any doubt, please post that thing into the discussion forum, and we'll discuss it there. So with that, let us conclude our session today. Um, and this was the last session what, and this will be available on the YouTube. I hope you are seeing this in the YouTube. With that, let us end it here. uh, Best of luck for your examination. Thank you all.